Hi, today I'm going to try and repair this classic floppy disk drive. I actually have to repair it because I blew it up during one of my previous videos. And it's been about 6 months and it's time to get this thing working. What happened is I took a HXC emulator and I shorted it out against this main board on this drive. And ever since then, the drive spindle motor doesn't turn anymore, but the head motors seem to go back and forth. So I've blown something up that causes this motor here to no longer run. So let's take a look at this, see if we can get it to work. I'm really lucky in a way because I've got a video of how I blew this thing up. Let's take a look at that video and try to get some evidence and, try to figure out what actually went wrong. Go to the HXC unit and check it out. So I'm going to try to get it so we can see it in the camera here somehow. My apologies, there's cords everywhere. Oh, wow, no. So based on that video, we could sort of see it in the scene, the scene's looking here and we can see this capacitor on the video. So there's some smoke coming from this general region. I'm going to guess, because this is discrete components, that the damage hopefully will be isolated to that particular zone. Looking at this general area, the most interesting component is this big power transistor. The motor that's not working is right on the side here, and that power transistor is sitting right next to that motor. So I'm going to guess that that is switching on power to the motor, which makes me think that that transistor could have failed. However, when we looked at the video, we saw that the smoke was coming from back behind here. So this may have failed incidentally, but there's a component back here that let out some smoke. So let's keep looking at these and just see what we got. These capacitors, they look good. This capacitor looks fine. It doesn't look like it's smoked. This transistor here, doesn't look too bad at all. It's of course going to be a bit hard to see that on the camera, but yeah, it doesn't look like it's smoked or anything like that. This little guy here, it looks like that's an inductor. Looks fine. I don't really see any damage offhand. What I'm going to do is I'm going to guess that maybe either this transistor here or this one here has failed. So I'll test both of those and we'll see what happens with those. One thing to mention, just like looking at the circuit and what I am guessing is going on here, is that definitely this is controlling the motor. That's controlling power to the motor there. And then this transistor is somehow related to this transistor, controlling the current into this big transistor here. So I'm guessing, maybe this is the transistor that smoked, because the smoke kind of came from this region. So it could very well be that that's blown up. Yeah, let's test these and see what we get. So I'm going to check the base to collector. Looks good. And then let's check base to emitter. And that also looks good. Now the pattern's not perfectly clean, but with this being in circuit, there's going to be other components that are interfering a little bit with the signal there. Now let's test this transistor here. Maybe I'll turn this around so we can see it a little better. Okay, so we'll go from base to collector. Fine. And base to emitter also looks okay. So it appears those two transistors are actually fine. That's not the problem. Let's do a little bit of testing of some of these passive components on the board and we'll see what happens there. I'm using my LCR meter because I can do the testing in circuit, and most of the time it's going to give me reasonable numbers. So let's just test this capacitor here. That's supposed to be 10 microfarads. It's coming up as 100 microfarads, which is a little weird. And then I got this resistor here. Overflow on that resistor. So that's, who knows. This one right here, we're overflowing again. Oh, of course we're overflowing. Let's switch to resistance. Okay, let's try this resistor here. And we are getting some weird numbers. Try this one here. That resistor, about 8K, looks fine. Now this is an inductor, so I'm going to switch to inductance, and let's measure that. We got zero microhenries. That's not right for sure. And then I'm just going to test these capacitors here, see if get any more information. These guys here, what do we got? 100 microfarads and 100 microfarads, so those look okay. Looking at these components, these resistors here I couldn't get a reading on. This inductor I got a 0 microhenries, which is a little suspicious. And these capacitors seem okay. This capacitor is high, which is a little unusual. So it could be, you know, probably any of these 4 components here. Another thing I noticed actually is if you look at these plugs, it's hard to see, but there's quite a bit of tension when you unplug and plug in this Molex, and you can actually feel the board bend. And if you look at these, they look like the solder has disconnected. It's like broken there. So that could be an issue as well. I mean, it could be something as simple as no power getting into the board altogether. So I'll solder these up, fix them. They might as well be fixed, and maybe I'll test it again, see if it starts working. Now I'm gonna reflow this. And the last one there. Okay, looks good. And I'll fire that up, see if it actually works. I don't think it's going to solve the problem, but it'll prevent a problem in the future. Measuring the components wasn't really conclusive, so I had to look for a service manual. And to find the service manual wasn't that easy because, you know, this disk drive here, I didn't know who the manufacturer was. If we take a look at the drive itself, it is marked here, Texas Peripherals, which isn't a brand I'd really heard of before. So I had to take a look for it, and did a quick Google search for the service manuals for the Texas Peripherals drives, and there's none online. They're not anywhere. So I thought to myself, well, this is probably a clone of a Shugart drive. So I found the Shugart drive service manuals, and it's actually quite similar, but it's a different circuit, but the design's very similar. And so, okay, well, that was close. Wasn't quite there. And then I did a little bit more searching, and I found actually the Tandon drives looked exactly the same. They have the same exact plastic front plate. So I guess this was probably a Tandon drive, and I actually found some more information that told me that Texas Peripherals was a joint venture between Tandon and Tandy, where they were making these Tandon drives in Texas instead of in California like the Tandon drives were. So I pulled up the Tandon service manuals for I think it's a TM100, and it was really close, but it wasn't the same circuit. It was different, and different enough that it wasn't helpful in analyzing this drive. The information that was helpful is it kind of told me how it operated, but it didn't tell me how this circuit was actually connected up. So I did a little more searching, and I thought about it, and I was like, well, this drive, this color computer drive, was used in the TRS-80 Model 3 and was used in the TRS-80 Model 4. At least they appear the same. So I pulled the TRS-80 Model 3 service manual up, and it had the drive schematics. The only problem was it was actually the schematics for the Tandon drive that I'd already seen. So I looked at the Model 4 service manual, and what do you know? It actually has all the data for this drive. It's got a whole section on how this thing works, and it's the exact same disk drive. So I printed that guy out, and now I am armed with all sorts of good information on how this thing works, and most importantly, I've got the schematics. So now I can debug this unit one component at a time. This is the schematic I found in the Model 4 service manual, and this section right here is really the area of interest. The spindle motor needs to run at exactly 300 RPM, and in order to do that with varying loads and whatnot, there needs to be some circuitry to manage that process, and so this circuitry is exactly that. The motor itself isn't on the diagram here, but it basically sits right here. And at the simplest level, what happens is we get 12 volts coming into this point, and the power goes down this line. It is controlled by this transistor here, and then it goes into the motor, and the motor runs. Really simple. The base of this transistor is connected to an LM2917, which is a RPM to voltage converter. What happens is the RPM signals come in through these two tack lines, and they are converted into a voltage, and that's connected up to our transistor base. It's all pretty simple. There's some interesting points to the circuit. One of the things that I found quite neat was this part here. There's a 1 ohm resistor, and there's this transistor here essentially connected to both sides of that 1 ohm resistor. Normally a 1 ohm resistor connected like this is being used as a current shunt, which allows you to measure the current going on this wire. And what's actually happening is that this transistor, the base of the transistor, is essentially connected to this wire, measuring the current, and it will allow more current to flow through this line as this current gets higher and higher. Okay, so how does that help us? Well, what happens is when current starts to flow through this transistor, it'll actually pull down the voltage on this line, because basically the power is going to go here and it's going to go through a 100 ohm load down to ground. It's going to pull the voltage down on this line, which in turn is going to cause this transistor to allow less current to flow. What that does is that basically provides you your current overload safety. if you stick something into the disk drive that isn't a disk, you're not going to burn out your motor, because this circuit will actually cut off the power if something is actually blocking that motor from turning. So that's kind of cool. It's in there. The second part that I found kind of interesting was this little portion here. We have a coil and a capacitor going to ground, and this is a classic LC filter. So it is a low pass filter that's going to allow low frequencies like DC and probably up to, I think, about 5 kilohertz or something to pass on this line. And that is going to be used to prevent electromagnetic interference from the motor, and also probably to clean up the power supply a little bit for this motor, because the motor itself, we have a switching action with these transistors and whatnot, that can cause it to work in an inefficient manner if the power is not cleaned up. So that filter is basically in there keeping the power nice and clean. I'm going to trace through the circuit looking for the 12 volts and yeah, see where it ends. Maybe that will point out what component is shorted out or what component is broken. I'll start with testing for 12 volts on the connector, and I've got 11.94 volts, sounds about right. And looking at the schematic, the next component in line is L4 here, so I'll test it on one side, and we've got 11.94 volts. Things look good. I'm going to test it on the other side, and we have 0 volts. Look at that. That's our problem right there, or at least that's one of them. There is no power going through this inductor. This inductor has blown up, and maybe it's what released the magic smoke. I'm going to do one more test here, because I'm going to go and... No, I think that's good actually. So that inductor looks like it's gone. If I go to the next component in line, that's C35. I'm going to find C35. It's not this one. C37. This is C35, I think. Yeah, C35 here. Positive. And we got 0 volts still. So the current is going through from the power connector. It goes, directly into here. We've got voltage. And then on the other side we got no voltage. And then it goes into this capacitor here. And obviously still no voltage there. So this is definitely our problem. Now to fix this, I'm going to have to pull this board off. And there's these sort of weird little connectors here, that sort of a nylon thing that need to pop up. Let's see if I can do that with this. I'm not sure if I'm using the right tool for this. Put this out. See that in there. Let's pop it up. Come on. There we go. And pop up this one on the other side here. See that? Alright, come on. Lift it up. Not quite. This one's a little tougher. There we go. Got it? Okay. Now hopefully that just comes right out. Of course it doesn't. Those are in. I think with a little bit of motivation, these will come out. The center pin needs to be pushed right up. Come on. I don't like these. Why not just use some screws instead of these stupid nylon things? I guess there's really no one to complain to anymore. Texas Peripherals is long gone. Oh, there we go. So that just popped right out. Perfect. Let's get that other side. Do this upside down. Might be easier. And come on, you can do it. No. Come on. Maybe I'll try pulling. No. Working a lot less. Oh. It's out of alignment now. No, probably not. Ooh, that wasn't good. I'm using the wrong tool for the job. Let's try this again. There we go. It flew a little bit, but I got it out. Look at that. Okay, and I lost one of those little things. Evil little device. Pull the board up, and I want to do this without disconnecting, well, basically anything. I guess I will only disconnect that. Should be okay. And the drive's open, and there's my board. So we've got our inductor across these 2 points. Let's remove that and go from there. So the easiest way to do this is going to be to use desoldering braid. Sometimes it's good, sometimes it's bad. In this case, it's pretty good. It's going to be fine. And I'll just clean this up. Forehand. Done. Now, if you're using desoldering braid, you got to use flux. Otherwise, it ain't going to work. And you know, they don't really tell you that on the instructions for desoldering braid. They never tell you to use flux, but you need it. There we go. Apply our flux. And wait for the iron to heat up. It looks like it's warm. And let's start removing solder. Okay. Got it? Oh yeah, look at that. It's all nice and clean. Good. And remove the solder on this side. And it's all nice and clean. Go back to this one a little bit. There's just a little bit left there. Okay, I think we're good. Then I'm going to try and pull that inductor out. Come on, you can do it. You can do it, little guy. Okay, let's try plan B and try to push those pins out just a little bit. There we go, that one's disconnected. And there we go. I think we're good. And let's pull that inductor off. Come on. Some things are easier to talk about than they are to do. A little more flux. Somewhere I got a big container of this flux, and I really need to use it and not this stupid setup I'm using right now. Okay, let's try to suck a little more of that solder off. Okay, come on. You can do it. Go, keep a positive attitude. That's important, right? Gotta stay positive while you're doing this stuff. So otherwise, you'll lose your mind. Okay, that one is not connected. And this one, just trying to break that connection there. I think that one's good. Okay. This is a situation where this might actually be a good tool. Pull that. And let's try this again. Yeah, there we go. Ooh, look at that. Look at that thing. It just literally split in half. Yeah, take a look at that component there. It is totally broken right in half, and it's burnt inside. It's like just totally shot. And there's a little bit of wire there, and that's the coil of wire, and it's just burnt all the crap. Okay, I'm gonna apply some heat to those leads and get this thing out. It needs to go. Heat, come on. That, there we go. She's out. And there, that was easy. That one's out too. Okay, so the component's removed, and we need to replace it. Yeah, so L4, yeah, 5.6 microhenry. There we go, let's just take a look. L4 is 5.6 microhenry. I'm gonna have to wind my own because I don't have a 5.6 microhenry coil lying around, but that'll be easy enough. Just use some of this magnet wire. Okay, so basically I need between 3 and 4 winds of this toroid with the magnet wire. So I'll get a nice piece of this. Good old magnet wire. And then I just wind it through there. I'm going to do 3 turns and we'll see what we get. There, 1. And then I space them out nice and even as possible anyways, it doesn't really matter. 2. And 3. Okay, there we go. We got our coil done. 3 winds. Now I'll strip the ends and I'm going to test this to see what we get as far as inductance. Now, stripping this magnet wire is a pain. It's a nightmare. I like to burn it and then strip it. That can weaken the wire as well. It's kind of a bit of an art, stripping those things. The leads are a little long, so that's going to cause the inductance to go off a little bit here, but I really want to get it in the ballpark range more than anything else. And the conductor is also not perfectly stripped. And we've got 12.4 microhenries. I unwound 1 loop of this, so now I've got it going through 3 times through the toroid. Let's see what we get. We don't need much. We have 8.5 microhenries. 8.5 microhenries is probably going to be fine for this. Particularly when I cut these wires down, it's going to go down a little bit, but I am going to unwind 1 more loop through this toroid and just see what I get, because if it's really close to 5.6, I will use that instead. And we have no connection. There, that should work. And we got 5, 6. So actually that looks good. Once I cut those leads down, it should reduce just a little bit and we'll be golden. Okay, now I gotta solder this guy in. So I've cut the leads down a bit and just place that in there. in there. See if I can make this nice and clean. Solder it down. Okay, got this going here. Solder it. Come on. Yeah, I think it's connecting. Okay, it's in there. I want to push it down. I want to make sure it some sort of physical tension there, holding things together, and pop that up. Look at that. It's like surgery. I'm a coil surgeon. Okay, and let's solder this. Okay. We have the solder, and it appears to have connected. Good. Looks like we're good. I'm going to clip these leads. Clip and clip. And we are officially done with that little repair. Everything's all mounted in there nicely, and hopefully we'll get some results when we plug this thing into power. I'm just going to dry fit this. Let's fire this thing up, see what we get. Let's apply power, and listen to that. I'm just going to put the mic up there. You can hear the motor is now turning, which is what it's supposed to do. Okay, let's give it a try. Let's drive 2, and there we go. And you can hear the drive going through the motions. So it looks like it's working. If we take a look at what happened, essentially I had that HXC unit, which is connected to power, and it's also grounded out to the power supply. We got our ground here. And the ground plane is going to be, you know, several points on this board. There's ground exposed conductor. And that exposed conductor, I accidentally touched to right about there. Now what happened when I did that was the power supply with its 12 volts started to basically conduct its full capacity through this inductor. And so that might be 10 amps, it might be 20 amps, who knows. But that passed directly through this inductor, and it went to ground until that inductor blew up. So the inductor blew up. And then at that point, it would no longer conduct any electricity. Therefore, this motor, which sits right here, no longer worked. I hope you enjoyed this video. And you know what, I really need the subscribers, so if you can find it in your heart to subscribe, it would be great. Need the subs, love the subs. Hope you can click that subscribe button. Anyways, thanks a lot for watching, and hope to see you next time.